Very good. Well, welcome to University of Pennsylvania's virtual conference on climate change. We've had a full week of discussions on this very issue from a number of different vantage points. And what I want to talk about today is a fairly broad range of issues. We'll review the science, the impacts, and the opportunities we have to make a difference in terms of climate change. Now, I have to acknowledge this is a fairly broad area, and any one of these probably would deserve its own individual segment, but I recognize that some of these are related, and I want to make sure I don't start on one area and leave it hanging in terms of the impacts it may have and the opportunities that will present themselves. So let's go through each of these. But first, I need to acknowledge that we're not talking about climate change. It seems too light and too inconsequential to worry about. We truly are in a climate crisis. And I think the sooner we understand that, the sooner we'll be able to respond and act in an appropriate fashion. Now, my objective for this presentation is to recognize that there are a number of people who have difficulties accepting the science of climate change and certainly its impacts. So what I'm trying to do here today is to address their concerns and their questions and try to illustrate what can happen if we don't act, and soon, and also recognize that, again, there are opportunities for us in pursuing this particular approach. Now, in terms of setting the stage, the situation that we currently have in the United States hasn't always been like this. Again, looking back in terms of what was happening in the 1980s, Nathaniel Rich, in his book, Losing Earth, A Recent History, as well as a New York Times article that he wrote August 1st in 2018, essentially outlined what had been happening in terms of our understanding of climate change, and more to the point, what has been the political response to this. Now, in 1980, hard to believe, but there really was bipartisan support for some action on addressing this particular issue of climate change. And statements were made by politicians that indicated that the main scientific questions were settled beyond debate. In 1981, NASA essentially recommended that the US use fossil fuels, oil, gas, and coal, as a bridge, only used as necessary to make sure that we would use that to get to the point where we needed to in terms of renewable energy. In 1982, Jim Hansen, who was then of NASA, held a symposium on climate change. And in that symposium, of all people, the president of research for Exxon stood up and said, "Capitalism's blind faith in the wisdom of the free market system was less than satisfying when it came to the greenhouse effect, aka climate change." And essentially his issue was that there weren't necessarily market drivers that would push us to do the right thing in terms of addressing this particular problem. In 1983, there was a presidential commission run by the National Academy of Science that confirmed the scientific consensus. Carbon dioxide levels were increasing, warming was continuing, polar ice was melting, sea levels are rising, and they did this under a title called climate change. So again, a very, very positive effort back in the early 80s. However, with the Reagan administration, they essentially put the brakes on this. They essentially said that it's not a big deal. We have 20 years to examine our options. And Exxon then changed their tune and said, free market's okay by them. And the American Petroleum Institute ended all of its research on climate change. They didn't want to essentially have it out there. And even though this was happening, there were still bipartisan bills dealing with global warming, aka climate change, that were coming forward. However, even though President George Bush had in his campaign said that we recognized the White House effect needed to be brought to bear on the whole issue around climate change, John Sununu essentially, again, put the brakes on it and said, this is not in our best interest, and he turned climate change into a partisan issue, where Republicans and Democrats essentially fell off on two different sides of this particular issue. And one of the things that was interesting was that there was a major effort and major investments in questioning the science by petroleum companies. And essentially a lot of that was to essentially focus on the natural uncertainties, the natural range of estimates that come out of the understanding that we have in this issue, to hopefully undermine the belief and support that we had bipartisan support for prior to this. So this is, this is not new. This is essentially the same tactic that was used with the issues around cigarette smoking, trying to, again, undermine some of the science that was relatively clear and straightforward. So that's the predicate for what we're about to do. So the big question for us now is, how do we get back on course? How do we change this? How do we essentially refine our way to essentially a more sensible approach on an issue that has potential catastrophic consequences, not just for us in the US, but for people around the world? Now, what I'd like to do is talk about sort of the broader issues of sustainability. And the brief synopsis of that is keeping mankind alive, keeping the human species going. Now, Gro Harlem Brundtland, who wrote the book Our Common Future under the auspices of the UN, had a much better definition, I think, and that is that we live today, we meet the needs of the present without compromising the ability of future generations to meet their own needs, i.e., we don't know what those needs may be, but we want to make sure that we act in a way that doesn't essentially foreclose their options. Now, sustainability also has three main pillars. One is economic sustainability, and there's debates about whether we can have responsible growth or even no growth, given the fact that populations may essentially flatline. Even though we see significant increases around the world, over the world since about the 1960s, we've seen a declining rate of growth, which means that the populations in the US and Europe are flatlining. And we see even China, probably by about 2040, 2045 will flatline. And India also will essentially see a steady state population by about 2065 or 2070. Now, there's also social sustainability. We have huge battles currently in the US where issues around equity are undermining a lot of the understanding of our social fabric. And there, of course, there are racial injustice issues, there are social justice issues. All of these things essentially need to be wrestled through and, of course, factored into our efforts around climate change. Consumption's an issue. Do we really need to have as many shoes, as many shirts, many pants as we do? War and peace, of course, is key and critical. And again, the issues around climate change can be a factor in terms of what happens with war and peace. And as I mentioned, social inclusion, living patterns. Do we have to live, work, and play in three different areas? Can't we come together and live, work, and play in one area, perhaps? Environmental sustainability, this is sort of where a lot of the debate starts. The issues around waste and pollution. And so as a result, we need to think about how we use our resources and also how we make our products in a way that can eliminate waste, that can use those byproducts in ways that are beneficial for other companies and other industries. So there's a range of issues that, of course, swirl in the background. But our existential problem is that of climate change. Now, in terms of the definitions around what is safe and what's not safe, a number of scientists got together a few years back in Sweden. And Jonathan Foley essentially wrote up their summaries and put that in Scientific American back in 2010, updated in 2015 with more of a range of issues. But nonetheless, in both of those, they saw climate change essentially having already passed, if you will, the boundary limits for the sustainability of not just mankind, but also of all those species. And also with biodiversity, that our expansion essentially comes at the adverse impact of the number of species that exist around the world. Ocean acidification is also on this. We haven't passed the boundary, but nonetheless, we do see the ocean starting to acidify, and that has ramifications in terms of shellfish and fish, which I'll talk about a bit later. And of course, chemical pollution's up there as well. Now, overall, the issues around environmental effects, putting aside the issues around carbon dioxide and other issues, are very complex. So you have a number of relatively straightforward activities that we all are engaged in. They, of course, have an emission of pollutants, and those pollutants have primary effects. And usually that's pretty much where we stop. But from those primary effects, there can be sometimes secondary effects, tertiary effects, and adverse feedback loops that can essentially make this a very, very complex picture. Now, climate change is a good example of what that's all about. Climate change, of course, is caused by a number of gases, greenhouse gases, carbon dioxide, methane, oxides of nitrogen, CFCs, all of them absorb thermal, i.e. infrared radiation. And this, of course, disturbs the balance of radiation emitted back to the universe. Now, the primary effect of this is to have a change in radiative forcing, i.e. with this radiation, you have the generation of heat. But it also has the effect, as we build up carbon dioxide in the air, that there's an equilibrium exchange between the air and the oceans. And as a result, you have lowering of the pH. And all of these are functions of the properties of the chemicals that we're concerned about. Now, the secondary effect from the increase in temperature, of course, is an increase in global temperatures. The mean average global temperature is starting to rise. And the tertiary effects from that increase in temperature is glacial melting, changed weather patterns, stronger hurricanes, all those things are out there. And of course, subsequent effects with different feedback loops are rising sea levels, impacts on biodiversity, agriculture, living patterns, current flows, fisheries, as I mentioned. And you have issues such as the Gulf Stream, which is potentially weakening in its strength. And that causes its own complications with respect to what happens in Northern Europe. Now, of course, the bottom line for us is what's the impact to people? And the impact, of course, is we could lose land and cities. We could lose a food source with fish and a reduction in foods in general in terms of the ability to grow grains where they're grown currently, but also a reduction in life years, i.e. the estimated expectation time for how long we're going to live. So with that as a precursor to all this, I have to acknowledge that our society has grown in the back of a dependence on fossil fuel. It's a clear focus of our economic development. Now, unfortunately, it's turned into a danger. Now, one option for us that we'll talk about later is that we can use less energy, but we can also switch to renewable energy, but with enhanced efficiencies for a lot of the different appliances that we use. I also need to recognize that countries around the world see their gross domestic product per capita increase with increased energy consumption. So politicians, companies all recognize that these are factors in terms of bringing people out of poverty, as an example. Now, I have just a very basic, simple equation in terms and an example of what happens with industrial activity. So by averaging a lot of different industries, we do know that for $1,000 of production on average, it requires about 0.19 tons of oil equivalent. And that's the combination of coal, gas, petroleum, but it's an equivalency. And for each ton of oil equivalent, it generates about 2.4 tons of carbon dioxide. Now, back in 2014, the world's economy was at 91 trillion. So if you multiply the GDP, that's 91 trillion, times the energy per production unit, 0.19 tons per $1,000, multiply that times 2.4 tons per, again, ton equivalent, you come up with about 41.5 billion tons of CO2 released in 2014. And this, again, a very basic question, this equation, this comes very close to what we see. Now, of this 41.5 billion tons of CO2 that was released into the atmosphere, about 46% of that stays in the air, about 19 billion tons of CO2. 54% of that is stored in natural sinks. So you have plants take it up, the oceans essentially take it up with equilibrium equations, forests, peatlands, all those things essentially serve as sinks, absorbing carbon dioxide. Now, with 19 billion tons of CO2 in the air, we also know that for every 7.8 billion tons of CO2, this essentially causes an increase in the concentration of CO2 in the atmosphere by 1 part per million. So therefore, in 2014, if you look at 19 billion, divide 7.8 into 19, you get 2.4 parts per million. Now, this isn't just a one-time occurrence, of course. This happens each and every year. So you have an accumulation, and it doesn't go away. It's not like water. It doesn't have a cycle around which it essentially washes out of the atmosphere. It stays up there. And it's not just CO2. Methane, oxides of nitrogen, CFCs, all those greenhouse gases contribute to this. So let me make the transfer now to discussion of climate science, a very brief overview. It has to be recognized that this really was discovered back in the 1800s. Joseph Fourier in 1824 came up with the idea that the Earth's atmosphere kept the planet warmer than it would in case of a vacuum. And we'll talk about that too. That's a very important predicate in terms of where we're going. In 1859, Eunice Newton Foote essentially ran experiments using glass tubes with those different gases exposed to sunlight and found, of course, there was heat generated from that. And so she essentially demonstrated in the lab a greenhouse effect. In 1896, Sven Arrhenius in Sweden essentially calculated the impact of doubling atmospheric carbon dioxide, which he estimated to cause an increase in global average temperature, surface temperatures of about 5 to 6 degrees Celsius. So the science, if you will, was pretty well understood in the 1800s. This is not something that's brand new, and most of the basic science essentially was determined at that point in time. Now, the other piece of the equation is that people many times, mistake weather and climate. Weather, of course, is something that happens in the now, here and now. It's essentially a set of phenomena that looks at temperature, humidity in one place and one time, where you have winds and rain and snow and all the rest of those things. Those are all relative to what we define as weather. It happens today. Climate is something that happens over a longer period of time. So we look at all of the various meteorological conditions over a region, and that defines the climate of that particular region. Now, one of the things that I should note here is that I'm not necessarily going to be reliant on models other people have done. What I'd like to rely on more pointedly is to look at the geologic record, because I believe that past is prologue. And as we can read the geologic record in terms of what had happened, we can understand what's going to happen in the future. Now, I'd also like to provide a relative point of comparison, and that is our own bodies. We know that, of course, if we're sitting at 98.6 degrees Fahrenheit, we're fine. Our temperatures are regulated. We don't have infections. We're not sick. Everything's good. We also know that just by a few degrees increase in Fahrenheit, we know we're in trouble. We start to recognize that there's probably an infection, an illness, something's coming on that essentially is attacking our body. And if that continues unmitigated, unrelated to essentially any other medical intervention, we recognize that at 107, you'll have brain damage and life-threatening. And in the same fashion for the Earth, we recognize that even though it's a relatively small increase in global average temperatures, it can have a significantly adverse effect to, again, floods, storms, crop failures, species extinction, ocean acidification. All of those things are continuing. We're at about 440 parts per million today, and it's rising at about 2 parts per million. And there's an expectation that by 2050, we might see a 3 degrees rise. And again, recognizing that people see this as weather, it doesn't sound that serious, but from an average condition, just as we compare it to body temperatures, this becomes very, very threatening for us. Now, Richard Revelle was a scientific advisor back in the Eisenhower administration, worked at Harvard, professor there. And Richard essentially asked Charles Keeling to do a very hard job, which was to go out to Hawaii, spend some time on Mauna Loa, and essentially determine the average temperatures that were happening as well as carbon dioxide levels. And this, of course, is the very famous Keeling curve, where you can see that where he's going back all the way to, this is records, of course, and his own measurements, going back to about 1880, where the Industrial Revolution started. The average global temperature was about 13.5 degrees Celsius. And of course, it's going up to something close to about 14.5 now. And you can see there's a good correlation with increasing carbon dioxide levels. And of course, we went back and looked at NASA's data, and of course, that goes back to 1880 as well. And again, the same sort of increasing temperatures is what we've seen. Now, we've used ice core data, and we've also then married that to what Keeling found in Hawaii, and find that for about the last 10,000 years, levels of carbon dioxide have been relatively flat. But since the Industrial Revolution, there's been a substantial spike, and you can see that red line. And just you should increase that red line past the confines of this particular box. Now, again, using ice core data, we can go back to about 500,000 years, and you can see there have been fluctuations here. I do want to describe those fluctuations. You can see about every 100,000 years, you'll have rises and falls. And they essentially define, if you will, both warm periods and ice ages. But you can see this is more substantial than anything we've seen, certainly in the near geologic past. Now, over the last 800,000 years, you can see the same sort of thing. So that just continued a little bit more. And again, with the Mauna Loa data, we're at very, very high levels compared to what had ever been seen in the last 800,000 years. Now, Fedorov did an interesting comparison of the CO2 levels, which are the red line, and the blue levels, which are temperatures, again, derived from ice core measurements. And you can see there's actually a very close correlation as these things go on, with a troubling issue as to what is going to be the temperature response to this absolutely significant spike of carbon dioxide that we see in the very near time. Now, I'd also like to talk a little bit about global warming. Clearly, there's radiation, solar radiation that's coming in from the sun, passes through our atmosphere, some of which is absorbed, some of which is reflected back into space, some of which is re-radiated out to space, some of which, of course, is captured by the very gases I mentioned. Now, radiative heat transfer essentially reflects the fact that these are electromagnetic waves. And radiation is completely independent of the medium. So it goes actually better in a vacuum. The best example we have is the warmth of the sun. And that's the one that people best understand, and it's the most commonly observed example. So radiation arrives on the Earth over a very broad spectrum. However, when it's reflected, it goes back at much longer, i.e. infrared wavelengths. And CO2 absorbs radiation, other greenhouse gases absorb radiation heavily in those portions of the wavelength. Now, it's not all bad. Part of the issue here is that we absolutely need a certain level of greenhouse impacts. It's life-sustaining. What we would find is that without greenhouse gases, the average global temperature would be minus 18 degrees C. And of course, that's opposed to what we saw at the beginning of the Industrial Revolution, where it was 13.5 degrees C. And that difference, that delta of the temperatures, reflects, if you will, the beneficial impacts of greenhouse gases. Now, just so we don't take that to an extreme, we have to recognize that all things come in moderation. And when you go to those extremes, you'll have problems. And so the climate crisis is really the recognition there's going to be an adverse impact on the Earth and our global ecosystem when that level of CO2 continues to rise above normal historical levels. This is just a graph that comes from the IPCC report, which essentially reflects changes in radiative forcing. And you can see, obviously, there are things that both support and detract from this. CO2, other greenhouse gases, all make that contribution. Things such as aerosols, cloud absorption, the albedo effect, all of that define it. But the net impact, which is the bar on the bottom, shows that our radiative forcing has increased to about, say, a little over 1.5 watts per square meter. So we recognize that there has been an increase in heating of the atmosphere that, of course, converts to an increase in temperature. Now, the other piece that I'd like to note is that different chemicals have a different greenhouse potential, a different global warming potential, GWP, and it differs over the amount of time. So methane, as an example, has a lifetime existence in the atmosphere, about 12 years. But again, over that period of time, it has a GWP of 72 times what carbon dioxide would have. And the same thing is true over 100 years, 25 times more. With CFCs, 11,000 times more. So all these things recognize that there are different impacts in terms of the evolution of heat from the radiation of these particular compounds. So the other question I've had is, well, why doesn't this heat just move into outer space? You know, we have an awful lot of weather, things do move around. We'll have convection, we'll have conduction, where convection, of course, is heat transferred through the mass flow of materials, and conduction is just, if you will, the perturbation of molecules, the collision of molecules that make up the material. But both of those require a medium, and therefore they can't necessarily be transferred to outer space, whereas radiation does not require a medium, so therefore it can come out. Now, the other piece, of course, is the ice core data. And just, again, very basically, when snow falls, it converted to, again, glaciers and ice, it picks up chemicals and particulate matter. And so as a result, there are tiny air pockets in that ice core that they can essentially determine from the analysis of the particles, the chemicals, and the gases as to what happened during that point in time. And they're able to essentially determine the time, literally, that that particular core is at by comparing that to the level of acidic sulfur, which is related in terms of its heavier concentration by different volcanic eruptions. So this is one of the ways that they're able to use ice cores to make a fairly accurate determination of what the temperature was, level of CO2 was, and the constituents in that air. Now, other questions that come up are around the issues of the Milankovitch cycles. You know, shouldn't we be in a period of glacial cooling? Shouldn't we be in an ice age? And of course, the answer is just on the Milankovitch cycles, we are in an ice age. You know, solar flares and sunspots also affect it. And we can look at that. Volcanic activity, we'll look at, and even agriculture. All these are questions that come up. But Milutin Milankovitch, of course, was the Serbian mathematics professor. His idea to start with was that variations in the Earth's orbit could have a major effect on the climate. He was looking, of course, over a long period of time in terms of ice ages and warming periods. And what he found was that the solar flux, the amount of heat that we essentially receive from the sun, in July at 65 degrees north can vary as much as 25 degrees over different periods of time. And this graph essentially, this picture essentially shows what he was looking at. He looked at the eccentricity of the orbit, he looked at the obliquity, and he looked at the precession of the Earth. Now again, the orbital eccentricity is the variation from a perfect circle, where essentially a perfect circle is 0 and 1 is an elliptic, parabolic escape, and continues to go to hyperbola. So that essentially changes with time, and he measured that. The obliquity is the axial tilt, and that runs between 22.1 and 24.5 degrees. And again, it just demonstrates how close and far we are away from the sun. Because you recognize in the summer for the northern hemisphere, of course, we're closer to the sun than when we go to the other side and we're further away. And of course, that's where we get our winters. So it's that, you know, annual change that, of course, affects our weather. And what he said was that that axial tilt also affects the climate on the planet. Now, precession, of course, is the change in the orientation of the rotational axis. So that it kind of wobbles a bit. And that's a span that ranges over a period of about 25,920 years. Now, this is a summary in terms of what we're looking at. Now, the bottom graph essentially represents the change in the Milankovitch cycles. So you can see, I remember I told you before we saw those changes every 100,000 years. That's in essence coming from the work that he did. And what we find is that when you're lower down on the Milankovitch cycle, you're in a cold period, i.e. you're in a period of glaciation. Higher up, warmer period. And so that changes again every 100,000 years. Now, the interesting part is that the last million years or so, climate's been driven by the Milankovitch cycles. And we can calculate what the climate should be given the amount of solar input. And what we find from his work is that we should be in a period of glaciation right now. So the basic question is, what happened? Why are we here? So the solar input has been dropping, but we see the other part of the equation is the addition of greenhouse gases, carbon dioxide, methane, and so on and so forth. Now, this graph, I think, is really extraordinarily interesting. If you look at this graph, you can see that about, 8,000 years ago, we had a peak warming, again, predicated on what Milankovitch determined. And from there, essentially, it's declining. That's that red line going past the glaciation threshold. So as noted before, we should be in a period of glaciation. However, you can see that yellow triangle, and that's the actual trend. And then, of course, the orange semi-square rectangle in the end reflects that little spike up in terms of what's been happening recently. So the big question mark is, what happened about 8,000 years ago? And of course, this is a reflection of human activity as well. So it's not something that just happened recently. So the determination now is what happened 8,000 years ago? And of course, what happened was our ancestors invented agriculture. We cleared the forest using slash and burn, which released a lot of carbon dioxide. For many cases, we used, of course, it was a swamp grass, which was rice, and of course, livestock. And both of those essentially generates methane. And of course, we used terracing. So a lot of the planet was really converted into terracing for the growing of different crops, especially in Southeast Asia and Asia for rice. So in the pre-industrial age, again, 8,000 years ago till just at the industrial age, CO2 raised from about 260 parts per million to 280 parts per million. This requires about 80 gigatons, a gigaton being a billion tons, of carbon. Now, this is also equal to about 10% of the existing vegetation biomass that existed back then, which we estimate approximates the early impact of agriculture. Of course, it reached a plateau. In order to continue to stay above that glaciation threshold, we needed more carbon. So we had to find a new source. Now, interestingly, agriculture couldn't keep up with that glaciation cycle. So things actually did get colder in medieval times. But the thing that essentially brought us out of that mini ice age was another source of carbon, which of course came with the Industrial Revolution. So again, the whole pre-industrial atmosphere had about 600 gigatons of carbon. With the Industrial Revolution, we essentially dug up coal, then of course, petroleum and then natural gas, and we burned those. And essentially that put a massive amount of carbon back in the atmosphere. So we were adding, as I calculated before, about 41.5 gigatons per year, with about 19 gigatons per year staying in. Most of this comes from fossil fuels. Now, the other question is sunspots. And what we see with this graph, of course, is that CO2 is increasing, the temperature is increasing, but sunspots are relatively not just flat, but they're also declining. So it doesn't explain away the increases in temperature. The same thing is true with solar activity. It did peak about maybe 1950, but after that it started to drop off with the temperature going up. So we can't necessarily lay blame to solar activity in terms of our increased temperatures. Another question came up with volcanic activity. Does volcanic eruptions impact long-term climate change? Now, we do know that when a volcano essentially blows its top, there's an awful lot of particulates that go into the atmosphere, and that, of course, creates its own level of climate control, because what that does is actually decrease the temperatures. But what we find, of course, is those changes are relatively minimal and short-lived. Now, there was an incidence of volcanic activity during the Little Ice Age and the Middle Ages, and so this also contributed to the fact that although agriculture had stalled and we had an overlay of volcanic activity, the mini ice age came, but of course we came out of that with the Industrial Revolution. Now, I also put a note here that this issue is also something that, if you will, foreshadows the plot in terms of what could be done with geoengineering, which could be either positive or negative. As far as agriculture is concerned, clearly a contributor, but again, they're man-made causes. But agriculture only emits about 5.6 billion tons, about 13.5% of our overall greenhouse gases. So this really can't be the sole culprit in terms of, but it's a contributor, and I don't want to dismiss that. Water vapor is out there. It is a greenhouse gas. The issue, however, is it doesn't build up. It doesn't accumulate in the atmosphere. It follows its own cycle. It resides in a steady state. Clouds are formed, rain falls, more evaporation. So it goes through that water cycle. So while it helps us live on the planet and it creates its own warming conditions, it doesn't necessarily cause the increase in temperature that we're seeing. Now for predicted impacts, and this is going to be a bit scary. And what I'd like to do is liken this to Dickens' Christmas Carol, and it's the ghost of Christmas future. I'm not going to suggest that this is what is actually going to happen. What I'm suggesting here is this is what could happen if we don't act. Now, of course, this means it's pretty aggressive. We have to essentially understand what's happening. But I also, again, want to base this on what happened to the planet in similar circumstances in past times, not necessarily just relying on models. They've been very good, they've been very accurate, but unfortunately things are happening quicker and they're more complex, and things are happening quicker than the models predict. So that is the one ominous sign here. Now, hopefully the devastation that we see, and we're seeing devastation now, we're in the middle of climate change, whether it's hurricanes, forest fires, elevated sea levels. There are a number of clear indications for us to pay heed to. Unfortunately, a lack of a response in the US to COVID-19 is an ominous sign, because if we're not able to essentially act, a lot of the things that I'm going to predict will happen. And the thing I'm going back to is something called the Paleocene-Eocene thermal maximum. That was about 55.5 million years ago. And it's when the planet warmed to about 5 or 8 degrees. Again, there was a general increase in CO2. But what that did, interestingly, was to trigger the release of methane from the permafrost that existed in the Arctic. And it creates its own negative feedback loop. So a little bit of methane is released, it gets a little bit warmer, more methane is released, it gets more warmer than that. So it continues to feed on itself. Now, the unfortunate part was that with that heating of the planet, 97% of all life on Earth died for a number of related causes, not just the temperature, but there are related causes to this increase, and I'll go through that in a bit. Now, mass extinctions, we've experienced about 5 mass extinctions on the planet, and it wipes the slate clean in terms of the evolutionary record. And it is, unfortunately, an analog for the future that we might face. Now, many people believe that those extinctions were the result of asteroids. And that was true, certainly, for what happened with the Cretaceous. When the dinosaurs were killed off, that wasn't greenhouse gases. That was, again, meteor impact. But for all the other ones, we believe that those all were related to some variation in terms of the greenhouse gas levels. Which leads me to the discussion of carbon and temperature predictions. Now, the Intergovernmental Panel on Climate Change, the IPCC, issues a series of reports, and they're usually defined as the gold standard of all climate research that's done around, because it's really a compendium of all the research that's done with the top scientists essentially coming together and essentially reviewing that. And of course, what they noted is that we're expected to hit about 4 degrees C of warming by the beginning of the next century. Should we stay the present course, i.e. no change in terms of how we live, no change in terms of the amount of CO2 emitted, everything continues. But I should note, that's a median projection. That is not essentially the range. And the upper end of that probability curves run as high as 8 degrees C. And of course, there are a couple of things that aren't necessarily factored in at this point within the IPCC's work. One of those, of course, is what do we do with permafrost melt? I mentioned what happened with the PETM. They're still struggling with how to factor that in too. They also don't deal necessarily well with the albedo effect. They don't look at cloud cover, which can trap heat. And they also haven't factored in the dieback of forests. So what would happen if we lost the Amazon, if there was a drying of the Amazon and a forest fire swept through the Amazon as it's doing in Australia and California? Of course, that not only releases more carbon, but it also detracts from the amount of carbon that can be drawn in from the atmosphere. So now the International Energy Agency looks at the same issue. And of course, what they've said is that we believe that the carbon dioxide concentration in the atmosphere, if we stay the current course, is going to hit about 700 parts per million, with the understanding that the resultant global average warming temperature will be about 3.4 degrees C, 50% chance, but it could go up to 6 degrees C, a 10% chance. Don't forget, I mentioned that sort of range of estimates. And the impact of both of those, of course, is going to be everything we've talked about: higher sea levels, lower ocean pH, a very different world than we know right now. So the other component within this is that they recognize that in order to control it to about 2 degrees C limit, we have to ensure that no more than 1/3 of our known fossil fuel reserves are going to be consumed prior to 2050. Now, of course, the downside of this is that stock price of big oil companies is related to their oil reserves. So what we're saying is that they have unburnable reserves valued at about $20 trillion, which is about 60% of their asset value. And to a degree, this explains why they've been a bit reluctant to come to the table and talk about that. Although, as I said, that's been changing. And I think there's some opportunities for them to make the conversion. And some companies are starting to think about how they can move away from being a fossil fuel supplier to being a renewable energy supplier. But nonetheless, their market cap is dependent upon those reserves, which is something they're going to have to grapple with. So the next issue I want to talk about is the climate change in the oceans. You know, what is really going to happen sort of across the board in terms of all the different effects, whether it's going to be rising sea levels, the impact of coral reefs, the Gulf Stream, and of course the global conveyor belt, and all those issues that essentially we worry about. Now, in terms of ocean level rise, which of course is usually the primary issue that many people think about when you talk about climate change, is that we probably should expect about 4 feet of sea level rise. And that, of course, is bearing any reduction in emissions. Now, what that means is if you're, again, a barrier island in New Jersey, sometimes their highest level is at about 3 feet, which means the whole island is going to be underwater. So, and it also means that a third of the world's major cities are on the coast. Power plants, ports, Navy bases, farmlands, fisheries, marshlands, rice paddies, all of those essentially have the potential not only to be inundated, but also to flood more easily because there will be weather patterns that are going to be much more disruptive. And so about 600 million people live within 10 meters of sea level today. It's a significant amount. Now, the unfortunate part is that a lot of the destruction that is going to occur is already baked in. There's nothing we can do short of being able to extract carbon dioxide from the atmosphere that we can do anything about. So Miami, Bangladesh, most scientists will assume that we're going to lose them within this century. They'll be underwater. Even if we stop burning fossil fuels in this decade, right now, stop it by 2030, they're still going to go under. 2 degrees of warming used to be considered the threshold of catastrophe. Now, the other big issue here is that that's going to have a significant impact on people around the world. And you're going to have climate refugees at a level that we really haven't seen before. So 2 degrees now is our goal per the Paris Climate Accord. And even at that, we're probably going to have a difficult time achieving that particular goal. The other issue we talked about in terms of the ocean, not only is the Arctic ice cap contracting, but also the thickness of that is thinning considerably. So it's essentially thinning out to the point where at some point in time, there's an expectation we'll be able to use those as navigation lanes. Now, in terms of the impact of sea level rise on everyone, it's estimated with, again, almost 4 feet of rise, which is what the estimates came back. It's going to impact about 4.7 million people in the US. And if it goes to the outer limits, the upper estimates there goes to 6 or 7 feet, it impacts about 7.8 to 8 million people. So there are some relatively significant numbers of people who are going to be impacted by this, again, by 2100. Now, the other piece, there's been some really good work by Susan Lozier and Ellen Martin that essentially looks at the global ocean conveyor belt. We talk about the Gulf Stream because that's the one we know most about, but clearly there is a large conveyor belt that essentially moves temperature and water around the planet. And this, of course, looks to be being impacted by climate change. We're seeing a diminution in the strength of the Gulf Stream, and from that, a worry about what that's going to do to the weather patterns. Acidification, I talked about before. And as you can see from the chart, the little cartoon on the upper side of the slide here, carbon dioxide exists in equilibrium with the water and air. So essentially it moves back and forth. So if you have a higher concentration in the air than you have in the water, carbon dioxide moves down. If not, it also moves up. Also, the water's warmer, you'll have more carbon dioxide being released, but obviously the equilibrium essentially is going to be more dominant. But if you have carbon dioxide blending in with water, you get carbonic acid, you get that acidic formation. Now, with that decrease in pH, more acidic, you're going to impact shellfish because with acidic water, they're going to have a hard time growing, holding onto their shells. Now, if that so shellfish may be eliminated. If that continues, fish themselves could have difficulty maintaining their bones. And again, that means a potential demise of the fish in the oceans. And I guess, again, going back to using a human analogy, if our pH in our blood drops as much as the oceans have over the past generation, it could induce seizures, comas, and sudden death. So this is, again, the analogy that I mentioned before. It looks as if we could have real problems in the ocean. Heating the oceans, of course, is significant because we'll see situations where the coral bleaching is going to occur, and it already has occurred in many situations, because coral need a certain temperature, and if it increases too much, they die off. And the reefs, of course, are very important, not just for the intrinsic value of the coral, which is important, but it also serves as a refuge for a quarter of all marine life. And that quarter of the marine life essentially then provide food to about 500 million people around the world. So this becomes very important. Now, there has been some research that looks at coral that is going to be acclimated to higher temperatures. And so there's some hope in that regard, but as the temperature continues to increase, we'll need to be careful about relying on that too much. Hurricanes, we have to understand that hurricanes pick up their energy from hotter ocean waters. It's one of the reasons when it swirls on through, and you can see it intensifying, it's because it's literally drawing heat out of the oceans and causing that weather pattern to intensify. Of course, this makes them much more destructive than ever before. Ocean toxicity is an issue that hasn't been discussed that much, but there is a feedback loop that exists here. And that is that if you have under-oxygenated waters, they breed a different type of microbe, which are anoxic. They live without air. So what that then does is create a feedback loop that is supportive of a dead zone. And that gradually moves to the surface, and essentially small fish die out, unable to breathe, and the anaerobic bacteria thrive. And so therefore the feedback loop continues in that regard. Now, in terms of these dead zones, there are dead zones already in terms of parts of the Gulf of Mexico, just off the coast of Namibia, really due to hydrogen sulfide generation. It's bubbling out of the sea along a 1,000-mile stretch of land off Namibia called the Skeleton Coast, called that because of whaling practices back in the 1800s, but nonetheless, it seems to be an apt name at this point in time. Hydrogen sulfide is so toxic that we have been trained, essentially, we have evolved to recognize it at its tiniest trace levels, and it's very quite critical. Now, they estimate, I mentioned before the issues around the PETM, they believe that the generation of hydrogen sulfide was partially responsible for that significant die-off of life on Earth at that point in time. And of course, there you have the issues in terms of feedback loops, killing off marine species that continues to feed on this. And so therefore, it just has a very significant potential. And even when it happened before in the PETM, it took millions of years before the ocean recovered. So continuing on the theme of just general issues around water, droughts and floods, droughts are bigger problems than heat because arable lands heretofore can turn quickly to desert. And precipitation is hard to model. We can have droughts in areas where today food is produced. And again, without some dramatic reduction in emissions, even Southern Europe could turn into what we saw in the US back in the 30s of a dust bowl. Now, in terms of Iraq and Syria, they're starting to feel some of that. There was some thought that aggravated the conflicts that existed in those areas. But even the breadbasket regions of China, South America, Africa could also be infected. So what we have here is that it could be an impact on them serving as any reliable sources of food. And of course, they're worried that there'll be droughts, even in the US and the Southwest, worse than anything we've seen in 1,000 years. And it's that sort of timetable where we believe a significant drought had an impact on the Anasazi civilization in Southwest US. Climate change and air, and of course you can see issues around forest fires, continuing pollution. But for us, we need oxygen, obviously. But as the fraction of carbon dioxide continues to increase, and it's already crossed 400 parts per million, what we see is with higher and higher CO2 concentrations in the air that we currently breathe right now, human cognitive ability, i.e. our ability to think and reason, declines by about 21%. And of course, the other compounding problem is that with increases in pollution, that also shortens our lifespan by about 10 years. So the other piece of that, of course, is the warmer the planet gets, the more ozone forms. And this is not the ozone at the upper stratosphere. This is ozone at ground level. And so therefore, Americans will suffer probably a 70% increase in the levels of unhealthy ozone smog predicted by the National Center of Atmospheric Research. And by 2090, the World Health Organization, WHO, essentially has identified that about 2 billion people will be breathing air above what they defined as safe. Forest fires are obvious. We've seen devastation in Australia. We currently see the devastation happening in the West Coast. And with that, of course, we see an adverse impact on health. About 10,000 people die each day from the small particles emitted from fossil fuel burning. However, with wildfire smoke, that can rise to about 339,000. And of course, it also means that the forest fire season is extended because of a lot of dry areas, droughts. So the U.S. Forest Service has indicated the wildfires will be twice as destructive by 2050 as they are today. And the areas burned could grow fivefold. I mean, the other part of the issue is not just that of forest, but even peat. Peat holds carbon dioxide, but peatland fires essentially have an adverse effect as well. Back in 1997, there were peatland fires in Indonesia, which raised our global CO2 levels by about 40%. And again, more warming only means more burning. So there is this negative feedback loop that happens there. And of course, the real concern is the rainforests in the Amazon also have an adverse impact. 2010, it suffered its second 100-year drought in the space of 5 years. If this dries out to a significant level, it could create devastating forest fires. Again, as I said before, it not only expels more carbon dioxide into the atmosphere and shrinking the size of the forest, but it doesn't take up CO2, and it also, interestingly, doesn't provide the oxygen that we require. And right now, it provides about 20% of the oxygen that exists in the planet. Let's talk about permafrost, the tundra that exists in the north. Obviously, the permafrost essentially traps a lot of organic matter, which decomposes and creates methane. But again, that methane is trapped in that permanently frozen land. Now, back in 2018, there was a string of days in the 60 and 70 degrees warmer than normal, which actually baked the North Pole, but it also impacted Norway's Svalbard seed vault. And that food bank was set up to essentially store all the seeds that we believe would need to essentially resettle and re-civilize the planet. And it was called Doomsday because it was just meant for that. If there was a real problem, thermonuclear war is an example. We'd be able to go to this vault and essentially extract the seeds and essentially create food sources for the people that survived that. Now, the interesting thing was that the permafrost that encased the seed vault seemed to disappear, which is that picture to the right. And this was only 10 years after it was being built. Now, fortunately, things did cool down. The Doomsday Vault is fine now. The seeds are safe, but it is a parable in terms of what's going to happen with the future. And again, the permafrost heretofore has not necessarily been a major concern because it was, by definition, soil that stays permanently frozen. Now, the Arctic permafrost contains about 1.8 trillion tons of carbon. That's about twice as much as suspended in the Earth's atmosphere currently. So when it thaws and released, that carbon evaporates off as methane. And as I mentioned before, greenhouse gases have a different multiplying effect. And methane is 86 times more powerful than CO2 over a period of 2 decades. And so therefore, if we lose the Arctic permafrost, we release twice as much carbon as is currently existing in the planet. And of course, the schedule with that's going to be released continuously moved up. And again, it's a negative feedback loop. A little bit of methane goes up, the planet gets warmer, more permafrost is essentially thawed, more methane is released, and so on and so forth. Climate change and health. This is very important, obviously. Now, first, of course, we recognize that we live in a global society. So there's clearly intermingling of human populations. It aids the transmission of disease, and we've seen that clearly with COVID-19. So global warming helps scramble our ecosystems. And now right now, if you're living in a temperate zone, you don't have to worry about dengue fever or malaria. But as the tropics keep migrating northward, we'll see mosquitoes migrate with them. And with those mosquitoes come malaria, dengue, Zika that continues to essentially cause problems for us. Zika is a good model for us. It reflects the impacts of disease mutation. And the other piece of that, of course, is not only will malaria move in, but we see that the parasite reproduces 10 times faster for every degree increase in temperature. And the World Bank estimates that by 2050, we'll see about 5.2 billion people dealing with malaria. Now, heat regulation is important. We're heat engines. We need to be able to cool off. And therefore, the temperature needs to be low enough to serve as a refrigerant for our bodies. The concern is that by about 2100, many portions of the planet's equatorial band will no longer be habitable. Humidity adds to that problem. Currently, we see in Costa Rica, as an example, that humidity tops 90% working outside at 105 degrees or higher. That's essentially lethal for people working out there. So this is a situation that could exist, again, all around the planet, around the equator. The other issue is an unusual one. And this, of course, reflects the fact that rock is a record of planetary history, but also, as I mentioned before, ice works that way as a climate ledger. But the other component of that is that in many cases, diseases can also be trapped in the ice, that as they melt away can release them, those diseases, the bacteria, now, or viruses. And it means our immune systems have no idea how to respond to those. They've been gone for so long, our bodies aren't ready to adapt to them. Now, the interesting thing is that many of these organisms won't survive the thaw, so we need to be clear about that. And it requires relatively significant lab conditions under which we've been able to reanimate them. So we see a 32,000-year-old extremophile being revived in 2005, an 8-million-year-old microbe brought back to life in 2007, and a Russian scientist self-injected himself with a 3.5 million-old year microbe. Now, I understand he lived and survived, but who knows what that was all about. But in 2016, a boy was killed and 20 others were affected when a frozen carcass of a reindeer, which was killed by anthrax, was essentially exposed 75 years after it died. And this essentially created this exposure of anthrax. Now, the other issue is food, and I mentioned this before. Clearly, at the present time, we live in a world with a lot of hunger. We recognize that even currently, we have about 8 million people globally who are undernourished. In the spring of 2017, there was a famine from Africa to the Mideast. The UN has warned, as a result of civil strife, that many areas in the world, Somalia, South Sudan, Nigeria, Yemen, are going to be subject to starvation because of the civil strife. But in addition to that, now we have issues around climate change. So we recognize that we have cereal crops that need to be grown at optimal temperatures. And that for every degree of warming, our yields decline by about 10%, with possibly as high as 15 to 17%, which means that if the planet is about 5 degrees warmer, we'll have probably about 50% less grain to feed 50% more people. We're over 10 billion people by 2100. And protein, of course, aggravates that. It takes about 16 calories of grain to grow a single calorie of beef, of meat. So we have this issue essentially, again, compounding itself. The other piece, of course, is that the presumption is, all right, if we have the planet getting warmer, we'll just move our crop growing regions up further and further north. Now, Rosamund Naylor and David Battisti came back and said, look, the tropics are too hot to grow grain. And also, if we try to move those north, the soil quality in remote Canada and Russia are not necessarily up to par. They're not going to essentially serve as easy substitutes for growing in, say, in the bread baskets in the Midwest in the US. And it's going to take literally centuries for the planet to essentially create the fertility of that soil that allows for the growing of those crops. Climate change and water, clearly a big issue, and war, I'm sorry. Because it has the potential of aggravating problems. Now, in terms of Syria, we don't necessarily put the blame on climate change in terms of the civil war that exists there. But we do know that climate change created a drought, which may have contributed to that civil war because a lot of the farmers were failing and they were looking for help from the central government, and it wasn't exactly forthcoming. Now, Marshall Burke, Solomon Chang went out there and looked at relationships between temperature and violence. And what they've seen, of course, that for every half degree of warming, societies will see between 10 and 20% increase in the likelihood of armed conflict. And putting armed conflict aside, we understand that, of course, that anything that essentially creates social conflict can more than double in this century. It doesn't necessarily mean it's armed conflict, but you're just going to have social conflict that's aggravated by temperature. Now, the military, of course, is not closing their eyes to this. They're concerned because there could be a number of problems for them. One, of course, is that a lot of our bases are close to sea level. They could be underwater. There could be a number of conflicts as a result of increased temperatures. And therefore, the elevated stress that we see is certainly even in the Midwest, is somewhat ironic and cruel because obviously it's from this area that a lot of the oil that we burn came from. In terms of war, sometimes it'll come down to agriculture and economics. Some of it will be due to forced migration. You know, we're talking at least right now, 65 million people displaced. That could be dramatically increased because of the inability of people to live where they currently do. And of course, there's just natural individual irritability. And the arrival of air conditioning might mitigate the impact on temperature, but it aggravates the problem of climate change because obviously it consumes more energy, generates more CO2, and again, it's a negative feedback loop. The issue of water is important. I mean, usually I'd talk about the glaciers that exist in the Himalayas and what happens to places, again, like India or Southeast Asia, when those glaciers go away. But something may happen before then, which are dams. Pakistan has dammed up rivers that flow into India. China, of course, has put dams on the Mekong. Again, for good reasons, I'm sure they're using it. But nonetheless, if any limitations on the flow of water into India or into Southeast Asia are throttled, this could provoke trouble. And that's on top, of course, of the loss of glacial melt. So, a very negative view. And as I said, hopefully this was the spirit of Christmas future and something that we can now avoid. What I'd like to do is shift gears and talk more about the hope we have and opportunities we have to combat climate. Now, the question, of course, is why don't we respond? In some cases, psychologically, it's just impossible to deal with this. The impacts are hard to imagine. It does require a new way of living, new energy sources, a new way of how we organize ourselves as a society. That becomes very difficult. The other issue, of course, is that in many cases, the scientific reports are coming out are not just hard to understand, but in many cases, and Jim Hansen essentially calls it scientific reticence. They're worried that they're going to communicate this in an alarmist fashion, so therefore they tend to downplay it. The other issue is that many technocrats believe that we'll be able to find a problem for it. And we'll talk about that in a second, but they believe any problem can be solved, and so why not this one? The other side, as I started off this discussion, is the imposing culture. We're seeing a real partisan divide in the US and probably in other countries, where if you believe it's X, they'll believe it's Y. And so we have that battle and that debate right now. Some is climate denialism. That's just because it's almost impossible to believe, and it could potentially impact your pocketbooks. If you own a lot of stock in ExxonMobil and you recognize that your stock price and the use of those reserves that they have are linked and tied, and they're prevented from using those reserves, you might want to deny that too. So that's understandable. The other, of course, is just the nature of it. It's happening both fast and slow. It's not necessarily something that's like a hurricane crisis that hits us in one swoop, but it happens over some period of time. But nonetheless, it's happening quicker than we might have the ability to respond and change to it. Now, I'd like to talk about Jim Hansen. He, of course, is one of the stellar scientists that have focused his career on climate change. He first started off studying Venus. And of course, the estimates there were that it was a very much Earth-like planet, plenty of water, but they had an issue of climate change where it literally transformed itself into an arid and uninhabitable, unbreathable gas. So he recognized that that was a possibility, but then he looked back at Earth and said, look, this is happening here. Perhaps I should shift my studies to what's happening on the Earth. So in his first paper in '81, he came back and said, things are happening, and we're going to see those things happening during our careers, our lifetime. Now, I should note that Hansen is an optimist, as are most all climate scientists. But it's not because they see this thing going away. It's because they believe that at a certain point, society is going to recognize it and act accordingly. And hopefully, this talk is just an example of that. So, unfortunately, they understand that in order to meet the Paris goals by 2050, we have to cut our carbon emissions by half each decade. So a half by 2030, a half again by 2040, and a half again by 2050. Emissions from land use have to zero out by then. And we also have to recognize we have to find some way to extract about twice as much carbon right now as plants do. So again, we have a lot of big challenges ahead of us. Scientists have a tremendous faith in the ingenuity of humans. This gets back to the technocratic solution problem, I suppose. They point to the Apollo project. They point to what we did with CFCs and the hole in the ozone. The issues around a thermonuclear war in terms of how we dealt with that in terms of mutually assured destruction. And of course, their conclusion is we'll have to find a way out of this. We have to essentially deal with this because any other approach, any other alternative is completely unimaginable. So now, the solutions, if we want to cut our greenhouse gas emissions, it looks like the conversion from fossil fuels to renewable energy is going to be somewhere in the neighborhood of 1.6 to 3.8 trillion dollars. A lot of money, but something that certainly could be done. Carbon capture, maybe 120 to 140 dollars per ton of CO2. So aside from these costs, the question is, are we going to really get there in time? So now, what can be done? Clearly, as I mentioned earlier, we need to decarbonize. We have to look at greater efficiencies, low carbon electricity. We have to switch from burning fossil fuels to using renewables. Now, the cost of climate change, the NRDC comes out and says, we believe the US alone will see an impact of about $1.9 trillion per year, which is just a little bit less than 2% of our GDP by 2100, which I think is manageable. The UN said the cost for fixing it, again, 1.6 to 3.8 trillion. General estimates are about 100,000 tons for carbon. And the USOMB says we've only spent about 153 billion, which is not enough to essentially combat this issue. This is an estimate in terms of the cost of action versus inaction. And obviously not just by 2100, but also by 2200. The damages that are going to be inflicted on society are going to be truly significant in the range of trillions of US dollars. But I don't want to just put this in economic terms. Clearly, there's going to be a human cost of all of this. And unfortunately, it's the poor that will bear the brunt of this in terms of the shortage of water, the impacts of floods, rising sea levels, droughts. All these things create migration and instability on a scale that we haven't seen before. So now, one of the things that have come up in terms of a possible solution, which is potentially problematic, is solar geoengineering. And that, of course, is adding particulates to the upper stratosphere to essentially reflect that sunlight before it hits the Earth. Usually calcium carbonate, calcium sulfates. This doesn't necessarily tackle the issue of acidification, but hopefully at least deals with the issue of temperature rise. At Harvard, they have something called SCOPEX. It's Stratospheric Controlled Perturbation Experiment. They have about 16 million on it, including money from Bill Gates. And their total estimated cost for doing this would be about $2.25 billion per year for about 15 years. There have been conferences on solar geoengineering. Stanford had one in September of 2019. The issue, of course, is the risk is huge. It might be a magic bullet. It might be the solution. But if you get it wrong, we go too much the other way, all of a sudden we go from being overheated to being overcooled. And we go into a period of glaciation. So that becomes its own, problem. And of course, with all of these things, the environment is very complex, and there could be byproducts that even now we don't fully understand. So there could be a lot of scope for trying to understand this. The problem with this is that a small country could actually do it on their own bat. They could do it on their own without any other approvals. And that creates its own cascading effects. So, and sometimes you see situations where one country could do it in order to thwart the ambitions or the interests of another country. So it serves as a form of virtual warfare. And it, of course, creates its own issues in this regard. Now, in terms of financial impacts, the US Commodity Futures Trading Commission said climate change poses a major risk to the stability of the financial system and its ability to sustain the American economy. And their first recommendation was we should put a price on carbon. If we priced carbon, people would act accordingly, and we could see some real change here. Economics will drive the proper behaviors. What it also says is all federal financial regulatory agencies should incorporate climate change risks into the mandates and develop a strategy for addressing these risks. It asks that regulators require companies to disclose Scope 1 and Scope 2 emissions, and think about essentially how we can go to Scope 3. Scope 1, of course, what happens for power plants coming in. Scope 2 is our own companies, and Scope 3 would be the supply chain. All of those things essentially are part and parcel of what we're going to consider, but they certainly also want to make sure that there are material impacts. And of course, their conclusion is that they probably will be. Now, the Financial Stability Oversight Council should incorporate these climate change financial risks into existing oversight functions, and financial supervisors should require banks and non-bank financial firms to address climate-related financial risks through their existing risk management frameworks. And that's essentially what's going to be incorporated into sensible corporate management. Now, the other flip side of that, of course, are opportunities. Someone could do well by this. The business opportunities are estimated by the New Climate Economy in their report of Unlocking Inclusive Growth in the 21st Century of being about 65 million new jobs worldwide and about $26 trillion worth of growth. Now, the opportunities fall into about 5 categories: clean energy, i.e. the transfer from fossil fuels to renewables; smarter urban development, more compact, more coordinated cities; sustainable land use in terms of how we grow our food and how we develop our forests; wise water management to address the issues around adaptation to droughts and floods; and of course, as I mentioned before, a circular industrial economy where we decouple economic growth from material use, drive decarbonization, but also create a situation where we recover as much of the resource we can from discarded products and reincorporate that back into new products. So what can industry do? Obviously, first and foremost, look at mitigation solutions. And many companies are starting to do that. They're starting to make projections in terms of what can be done and what can be achieved in terms of carbon neutrality by 2050, 2060. Adaptation as well. How do we essentially adapt if some things go wrong? The other, of course, issue is they switch to renewable energy sources to achieve carbon neutrality, as mentioned before, develop energy efficient products, not only in their own operations, but the products themselves have to be energy efficient, and develop systems to develop a circular economy, have reverse logistics efforts where you go out and recover those materials and reuse them. Now, I was involved with 3 different studies working with Accenture. We did a mitigation study for a UK company where it looked at a project by project, year by year design for carbon neutrality, which we were able to essentially achieve. Adaptation, we wanted to see if there was a problem with respect to disease patterns and related to climate change. And we worked with universities around the world: Oxford, Cambridge, London School of Hygiene and Tropical Medicine, Harvard, Columbia, Hamburg, Nehru, Australian National University, as well as Care and Path. All of those people made a contribution. In essence, they looked at those patterns with the understanding that this could inform what happens within research and development to see if they could essentially start to deal with the diseases that may come in the future and avoid the situation we're in right now, as an example, with COVID-19. We're struggling to catch up. Now, the other piece of that, certainly with the mitigation study, was that we had to make something real. It had to be tangible. And so we recognized that laboratory buildings, because of fume hoods primarily, were very difficult buildings to achieve carbon neutrality. So we put together a design team and looked at creating a design that would achieve carbon neutrality. That design, as well as some funds, allowed the University of Nottingham to build a sustainable chemistry lab, which was carbon neutral, not just in terms of its operation, but through its whole life cycle, from extraction to its end-of-life use and dismantlement of that building, if it ever comes to that. Hopefully that building will last for a good long time. Now, what can universities do? Clearly, there's 3 big things, I think. One is to create research institutes on climate change. Multidisciplinary studies, bring the best people together and have them working together, which is, again, a complete departure from what universities normally do, where we all work in silos. We can develop undergraduate and graduate degrees to focus on this problem, both in terms of sustainability and certainly on climate change. We can also set as an example and use operations at universities as living laboratories. The drive toward carbon neutrality, or beyond that, and going carbon negative. And look at such things such as the Living Building Challenge to serve as a template in terms of what can be done. What can governments do? Clearly, you want to educate the public. You need to send a clear signal out there that carbon change is real and very problematic if we don't act. Stop fossil fuel subsidies. That's just going in the wrong direction. We could enact a carbon tax with an understanding you probably need subsidies for the poor, because this would be a regressive tax. So therefore, we need to subsidize the poor and hopefully have that subsidies be redirected toward renewables, not just paying off their gas bills. Fund research and certainly encourage innovation. And this is something all governments around the world can do. Now, interestingly, on September 22nd, Xi Jinping gave a video message to the UN General Assembly. And what he said was that China is going to halt the rise in carbon emissions by 2030 and achieve carbon neutrality by 2060. Now, of course, by talking about carbon neutrality, he's relating this only to carbon dioxide, which represents about 20% of all carbon emissions around the world. So not a trivial issue and a big, big step forward. In 2019, the EU proposed climate neutrality, which relates to all greenhouse gases by 2050. Now, their emissions peaked in 1990, again, not 2030, but it hasn't been formally adopted. But this would represent about 10% of all CO2 emissions. In the US, carbon emissions, interestingly, peaked at around 2006. It's dropped by about 14% since then to now. And of course, the US would need to develop a similar target and timetable to what the EU and China have already come up with. And that, I think, would also serve to rally the rest of the world. The rest of the world's looking for the US to provide some leadership in this regard. And it hopefully will not only encourage and incentivize what we do in the US, but also create that as a platform for action around the world. What can students do? Clearly at Penn, we have Fossil-Free Penn, which essentially asks the university to take monies from their endowment out of fossil fuel companies. I do support this. Climate change is real and an existential threat. In terms of equity, the poor people are impacted more than people who are more well off. The investment, of course, is just a bad deal. If the Paris Accord goes through, as I believe it will, all those oil companies that Penn has invested in will have stranded reserves. And therefore, and the stock price has already declined over the last 5 years from 87 to 37 by 2020. The other piece of that, of course, is that the university has a responsibility to its own students. And our students, our generation is going to be, their generation is going to be impacted in their lifetime. And so therefore, I think it's incumbent upon the university to take action along these lines. Now, what can students do? Clearly, you want to be aware of your personal energy habits. You want to support government action to provide sensible climate policies, vote for candidates who support climate action, demand climate-sensitive products, petition universities to do more and lead in this issue, not to follow, and recognize that we're in a climate crisis and we have to essentially do something together as a society, coordinated and in a systematic way to be able to address this so we can avoid that very dire and grim future that I portrayed in this presentation. Thank you all very much for your time. I thank you again for participating in Climate Week at the University of Pennsylvania. Take care, and I will hopefully see you for the next presentation.